And so in a covariant version of Nijmegen, we have a different object, which is the purification co-presheaf, which you'll also know what it is, so I won't spend too much time here. So the idea of introducing the spectral presheaf, the original idea is that you should regard it as a state space for the algebra, for the non-commutative algebra, and this should generalize the Gelfand spectra in the commutative case. And as such, it should be a topological object in some sense, in the same way as this co-presheaf is an algebraic object internally in the toposophy. And also, if we talk about duality proper, so if we want to talk about morphisms as well, so if we have a star homomorphism between two C-star algebras A and B, this induces a map between the spectral presheafs in the opposite direction, and we want this guy to be continuous in some sense as well. And so again, in the covariant presheaf, there would be a map in the same direction between the two co-presheafs in some sense. So we'll see. Slightly different motivation for considering these topologies on spectral presheaf is that so from the original papers, or at least from the during Eichhorn papers, there's this Dasnization of projections. I'm not sure if that comes before. Okay. So there's this Dasnization of projections, and which is done for the case of von Neumann algebras, and you take projections of the algebra and you approximate them in each classical context, and then you consider a Klopen subobject that corresponds to this projection, a Klopen subobject of this spectral presheaf sigma. But as Dan pointed out, and he's proved this, that not all Klopen subobjects of this spectral presheaf can be generated. By touch that. So not all Klopen subobjects are generated from these ones, these Dasnized ones. So maybe it's also interesting to consider this topology just generated by the Klopen subobjects. And so this might motivate why you want to consider different topologies on sigma. Okay. So our definition of what is a topology here, I'll just give a very elementary definition, and I'll point out some things. So we'll consider a topology defined by closed sets instead of open sets, and this makes certain things easier. So we'll just consider that for now. And so such a topology on a presheaf is basically a collection of subobjects of that presheaf that includes the zero and top and are closed under whatever they should be closed. So in this case, as we consider closed sets, it should be finite tree intersections or arbitrary intersections and finite tree intersections. And
so to be clear, so sub P is the external family of subobjects, is it? It's not the internal power object.
Yeah.
Yeah. Okay.
So you consider all the subobjects of this thing. So you could consider analogous definitions with open sets or with Klopen sets, and it's pointed out by John Funk that we could define this in a different way. But as I said, this definition is rather external, but I think it relates to these spaces that come from this old paper of Eek and Modak. And so there is a difference between these things. So one difference that he considers, so these spaces are internal topological spaces, and they're basically taking the definition of topological spaces, interpreting the internal language, and so we consider the definition of topological space by open sets, and here we're interested in closed sets, but that's a minor difference. But there's another thing that has to do with the direction of morphisms that seems, so especially when we're talking about having different, when you're talking about having different base categories, so the direction of morphisms that he has seems to be different from the one that we have here. And so there's something that's not quite clicking there, so I'm not quite sure yet how to connect these things. Anyway, so one example of such a topology, a very trivial example, is that if we have a presheaf that's valued on topological spaces, which is the case of the spectral presheaf, you can just say that a subobject is context-wise closed if it's closed at each context, right? That's a very trivial thing, and this does define a context-wise C topology on P when you interpret P as defined in sets. But I think there's also something on this paper on space spaces that sort of says that you can regard all of them in some way as top-valued sheaves. Something of the sort. So, but in particular, there is such a context-wise topology on the spectral presheaf, which is the one that we'll mainly consider. So this is the one that we'll mainly consider. So as I said,
is it true that if you have a global C topology, it uses topologies on all the components?
Yes.
You have a set value presheaf, but you have a C topology on it.
Yeah.
And all the components become topological spaces because in the C topology the operations are defined in each context.
Mm-hmm.
So in this sense, every
so
this
that's something that's in Ike's paper about space spaces. So I think it applies.
This is why they all talk about it.
Yeah.
If the notion of topology comes.
Right. Anyway.
Yeah.
So now I need the board. So another bit of this has to do with Dazzleization. So there was this idea that from Dazzleization of projections you can generate certain Kloben subobjects, and these will generate such a topology on the so that would generate such a topology on the spectral presheaf for Neumann algebras. But so I'll just present very quickly why this can also be done for C-star algebras in a very easy way. So this is kind of a slight detour from the rest of the talk, but it's just a generalization of this Dazzleization of projections. And so I'll just use the board because I need to draw a few diagrams. So the original idea of Dazzleization is that suppose we have two complete lattices, and we have an inclusion of complete lattices, and so in particular this guy could be the projections on a Neumann algebra, and this guy could be the projections on a abelian subalgebra, self-Neumann algebra. And so whenever we have these, there will be can you read here? Is that possible? Yeah, thank you.
Wow. It's not
Thanks.
wake up.
Wait,
Wait.
please.
Yeah, so the idea is that you can get, so there's a left adjoint and a right adjoint, and these are called the unidization and the altidization. So it's basically an approximation from below and approximation from above of the projections there, or the elements of that lattice, or the elements of this lattice. And then what you do in terms of so what you do is you do this for all abelian subalgebras, and this kind of generates so this gives you a projection, an approximate projection, either by outidization or by indization on each subalgebra. And this then corresponds to a Clopen set, because you can I will just see here that if you have so you have 2 billion algebras, 3 billion algebras, one's including the other. So this could be the projections of some v prime, and that could be the projections of some other v and v prime including v. And so the elements of this Boolean algebra correspond to the Clopen subsets of the spectrum of that Boolean algebra, right? But they can correspond, so I'll just write it twice, because we could do this in 2 ways. So what you need is, so you could either, so I call this guy J, and this guy K. It is quite obvious what you can do is, so K of some element B is just all the taus in SB that assign 0 to that element, whereas JB is just a complement of that, so they assign 1 to that element. Right? But either of these would be a Clopen subset of the spectrum, and you can go either way. So right? Yeah. That makes sense now. Okay, and here is obviously there's an op there, because this guy, one is complement of the other. So. And similarly, you have the same thing here and there. And so what we have with outidization, so outidization is this left adjoint here. And here we have the inclusion, and the inclusion will correspond in each of these things to so if you have an inclusion, so you have an inclusion of B prime in B, right? And this will give you a map between, so that the stone dual of that is a map between SB and SB prime. And so, and this inclusion here in terms of the elements and this correspondence with Clopen sets will correspond to this taking the eveness image of the map here and there. And so this outidization, which is the left adjoint, is also the left adjoint there. And it's the right adjoint on this side because we have this up there. And so, well, the left adjoint here is just the forward image and then closure, but as these guys are closed maps, this is actually just the forward image, and the guy in this side is the forward image, and then take the interior. And one sees that if we want to have Clopen subobjects in the spectral presheaf, we need to use this side of the thing. without a Latinization, because we need to go, if we have some clopin subobject corresponding to a projection there, we need to go to a bigger clopin subobject in this smaller algebra. So we need to go through something that's bigger than this row. So if we have some subobject there, S, then the subobject in here must be bigger than the image by row of this S. So we need to use this side of the thing. On the other hand, if we do inner-Latinization, so maybe I don't have colors, but if you do inner-Latinization, we should do this side of the picture. And just do that. Then here is also this side of the picture, and on this, and here will be the left adjoint. But now we have interior composer row, and there we have closure composer row. So when we want to use inner-Latinization to define a clopin subobject, we have to use that side of the diagram. Right? So we have to use this correspondence by K. You see, we have to use a correspondence by J. So the point now is that so we want to do some sort of analogous thing for the case of C-star algebras. So we'll just first consider this, so a very similar thing, but where now these L prime and L are not necessarily complete lattices, but just yeah. So just well, they're so just lattice. So this guy is included in there, and then we can take the ideal completion of these lattices. L prime and L. And there'll be some inclusion there, but this is just going to be a morphism of complete joint semilattices. I hope I'm getting the German meets right. I think so. So this means that we only have one of the adjoints, so we only have the inner Latinization there. We don't have the outer Latinization anymore. Of course, if you take fill to completion, then you could get the corresponding thing to outer Latinization. And right, so what you can do now is that. So now we consider the Boolean subalgebras, where we have ideals of B and ideals of B prime. I have this inclusion there. And again, these ideals can correspond to the opens. Or they can correspond to the closed. Subset of B prime. So in much the same way as we had before, the K and the J, because you say that they're zero, but they're different from zero on that particular idea. And here you'll also have some sort of the same thing. So nameless image will be what corresponds to this inclusion. And now we only have the inner Latinization. So we only have these adjoint. And so here we have this right adjoint, which is interior composed with the forward image, but on this side, because of the op, we get a left adjoint, and this is the closure composed with a forward image, which again, because the map is closed, is just a forward image, that doesn't matter too much. And yeah, so the point now is that if we want to get some subset of the spectral presheaf, or subobject of the spectral presheaf, we need to use this side, because again we need to go to bigger things when we go down. And so so the natural thing is that an ideal of this, of a lattice, say if we come, will give you a closed subobject of the spectral presheaf by using this inner diagonalization. Of course, you could, if you take filter completions, you'd get outer diagonalization, but again, you end up having to use the closed bit because basically because this in the filter completion you get a knob as well here, and so that makes you also use the closed. So both cases will give you closed subobjects of the spectral presheaf, and that's why we were considering closed things. So I'm not sure if you change the variance of the thing, maybe you can consider the opens. There's maybe not much difference. But in this case, it makes sense to consider the closed. And so obviously, you can do a similar, so a very similar picture for algebraic ideals. So if you take a C-star algebra, you can consider take any ideal of the C-star algebra. So you can consider all the right ideals or all the left ideals, or the two-side ideals, doesn't matter, but any of them you can diagonalize and get ideals of the sub-algebras, and which are basically just by intersection with the algebra. And these will correspond to closed sub-objects of the spectral presheaf for the C-star algebra. So this is sort of a generalization of what we have for von Neumann algebras, but here we have less. Thanks. Okay. So now we have less structure than in the case of yeah, so we have less structure in the case in von Neumann algebra, so we can only do the inner diagonalization of ideals, but we still can get some closed, context-wise closed subobject of the spectral presheaf from this idea of diagonalizing global things, in this case the ideals of the algebra. And again, you can use this to define a topology which is not going to be a context-wise topology, but it's going to be something smaller. And you can maybe think whether this would be an interesting topology or not. So yeah, so far we didn't quite too much with it, but anyway, so let's just carry on. So close this detour to diagonalization, and we also again considering these presheafs equipped with these topologies given by closed subobjects. And if we have two presheafs of the same base category, then it's easy to define what should be continuity between these topologies, right? So it's just if you have an alpha transformation between the two presheafs, then the thing is continuous if it's given a subobject of Q is in this image by an alpha transformation. So this pullback will be so given a closed subobject of Q, then this pullback will also be closed, a closed subobject of B. And so that's easy for when we have two presheafs over the same base category. And in particular, whenever we have top valid presheafs and we consider the context-wise topologies as we did before, so this notion just means that you have the natural transformation is made up of continuous components. So it means that it's basically the natural transformation on this. So here, so it means that every component of the natural transformation is a continuous map between the topological spaces. But now, in our case, we're mostly interested in maps between presheafs over different bases, because we have, so if you have two different algebras and we get the spectral presheafs or the purification co-presheafs, you have, I mean, there's two different base categories. There's two different base categories for these maps. So, so we need to know, first of all, what is a map between presheafs of different bases, and can we find a satisfactory definition of continuity for these cases. And this is not so easy for general topologies. It's easy if we consider these context-wise topologies. We can get away with something. So we'll just do it now. And right, so we just move to this last part of the talk where we just mention so how to map between presheaves or co-presheaves of a different basis, and how these things and some very simple remarks on how these things are dual to each other. So, what we want to have. So, we want to start from a star homomorphism between two C-star algebras A and B. And if we do that, it's obvious that we can get a map from the commutative subalgebras of A to the commutative subalgebras of B, right? And this is going to be our map that changes the basis. From A to B. And also, for each context C, we can have maps from V to F of V, and also, so by Gelfand duality, from sigma FV to sigma V. Right? So this will, so in the end we want to define, so starting from a star homomorphism between C-star algebras, we want to have some sort of map between the purification co-presheaves in the same direction, or between the spectral presheaves in the opposite direction. And so this thing will sort of justify, so this is what we're going to get, but there's a choice when you define.
Hang on, what's the relation between C and B there?
Sorry, this should be, everything is C or everything is V.
Okay.
So do the same. This type, so just put V there. Then it makes sense.
Okay, so C is a context for A.
Yeah.
Yeah.
So C or
Yes,
V is a
okay,
context for A.
yeah, yeah.
Sorry. Yeah, I think I had all these and then I tried to change the seasons. So let's suppose that we have two presheaves over possibly over different bases. So we have this presheaf Q over J prime and this P over J, and we want to map from Q to P, right? And we consider a map from Q to P to be a functor from J to J prime that changes the basis, and then a natural transformation between these two things. So if you have J prime going to D, and so this is Q, and from J going to D this is P, and so we consider a functor F. So the map consists of a functor F between J and J prime. And then a natural transformation, basically, so we use this map to pull back Q to leave over J, and then the natural transformation goes between this guy and that. So natural transformation between this guy over there and that guy over there. And so this allows us to define a category of, in this case, D-valued presheaves with such maps. And it's right, so that's like in reading the top of it. Yeah, so here is where I think there's a bit of a difference where in this spaces thing where when they consider a map from Q to P, they consider, so the natural transformation in the end is between P and something related to Q, not the other way around. And so this makes a difference when you talk about continuity, because here we'll be interested in, so the image of something closed in P should be closed in Q, or open, and that sort of makes things a bit more difficult, but the problem is this is the thing we need because we want to get these maps using these guys over there. Anyway, so analogously, so you can look at co-presheaves, and again you have a similar thing, and if you have a co-presheaf Q, so we should J off. So now we consider Q also over J prime going to C, and we consider this P over J, this Q upper bar over J prime, and a map between P and Q now is also a functor between J and J prime, and then an atom transformation between these P and the pullback of Q. Right. So I kind of switch it Q and P here to make it the next slide very clear, because now we have a category of co-presheaves valid in some any category C, and this is quite a trivial observation that if two categories are dually are in a duality, so dually equivalent, C and P, then the category of co-presheaves over C and the category of presheaves valid in D, so co-presheaf valid in C and presheaf valid in D with such maps are also going to be dual. And the way it works is simply by taking the dual of any diagram using the original equivalence. So we take, so a co-presheaf will consist of certain sets or certain, will consist of a certain diagram in C, and you can take the dual of it and I'll make a presheaf valid over D. And the way we define the maps will make the thing work as well, being dual to each other. And in particular, if we in our case, we have this duality between units of commutative sister algebras and compact household spaces. So we can consider, so we have also a duality between co-presheaves valid in units of commutative sister algebras, which is the case of this Bohr co-presheaf, and presheaf valid in compact household space, which is the case of the spectral presheaf, where with the maps are like that over there. And so for any C-star algebra, we have, by this duality, obviously the borified co-presheaf will correspond to this spectral presheaf. That's kind of obvious, but moreover, if we have a star homomorphism between A and B, we get a map between A and B, so according to this definition, between the co-presheafs A and B, that preserves the algebraic operation context-wise, so it's kind of a partial star homomorphism. And we also get a map between the spectral presheaves in the opposite direction, that is continuous context-wise as well. And so sort of this context-wise topology on the spectral presheaf captures the same thing as this being context-wise a homomorphism in the borification co-presheaf. So I mean this is not much. So it doesn't. So the two things are the same, right? And these are basically morphisms of partial C-star algebras. Yes, so so there's still the question of whether could we capture more than just that by adding some different topology or some more information to the spectral presheaf or to the co-presheaf, which will be the same thing as well. Also, because if we have, so there's a last point that I just want to make. If we have, so if we just consider a single base category again, so we're just considering a single algebra, and we consider the borification co-presheaf and a spectral presheaf, and so if you take these sliced categories, they'll also be dual to each other, and this means that if we have, so So if you have a monic like that, this will correspond to some epoch in the other category over there. And in particular, if we take these context-wise closed sub-objects that we're considering over there, these will correspond to maps that are quotient by ideals at each context. And so I think these are probably, you can probably say these are internal ideals in some sense, but I'm not entirely sure. So it seems like you can somehow translate certain contexts, translate certain concepts between the co-presheaf and the purification co-presheaf and the spectral presheaf in this sense. And, okay. Yeah, and I think there's also some correspondence between these closed sub-objects of the spectral presheaf that we've been talking about and opens of the internal local that you get in the covariant approach by taking context-wise complements. So in summary of what we got so far, so we consider topologies on the spectral presheaf, but in particular the only one we could actually do something with was this context-wise topology given by context-wise closed sub-objects. And so these topologies are kind of internal topological space in the same way, and show that this spectral presheaf is an internal topological space in the same way as the thing coming from modification is an internal system. And we also, so in this slide here, we extended the Dasnization of projections that works with polynomial algebras to Dasnizing ideals in sister algebras. We see that we can get closed sub-objects of the spectral presheaf from there instead of just a closed sub-object. So we get, yeah, because there might not be so many projections, so there might not be. There might not be more than just two closures. The empty set and the full set. So, also, in the end, we consider duality between this co-presheaf and this presheaf, both in terms of the maps between the spectral presheafs and the purification presheafs with the change of basis that we're considering over there, but also like these closed sub-objects correspond to ideals. And there's a question of whether we can take this a bit further as well. So a few, so as I said about the last part, there's the question of whether we can take this further and consider other interesting correspondences between the two approaches. Or about the first part, there's so we're not quite satisfied with the right definition of continuity for general C topologies, not just these context-wise C topologies. And the one that's so the one from the space-spaces thing seems, so the morphism seems to go the other way around. So we're preserving the topology on the wrong way. So we'd be preserving the topology, we'd be mapping the topology in the spectral presheaf of A to the topology in the spectral presheaf of B instead of the other way around, which kind of doesn't seem right. And also the kind of obvious way to define continuity for C topologies that we could get is a bit too restrictive. In particular, when we don't have when this thing is not injective, this functor that changes the basis, because you can, when you're trying to, so you're mapping from, say, the spectral presheaf of A to the spectral presheaf of B, but this, so from the spectral presheaf of B of B to the spectral presheaf of A, but to this F star of this pullback of the spectral presheaf, and if you just take the closed sets there to be the pullbacks of closed sets in the spectral presheaf of A, then this is a bit too restrictive because it forces you, so it doesn't give you the context-wise topology as you would expect. So the context-wise topology doesn't pull back to be the context-wise topology and the other thing. And but the question is still whether others, so if you can't find such a definition of continuity, is it interesting to consider other C topologies or not? And also in particular this Dasnization topology, we don't even know if the star homomorphism would be continuous with respect to this. Also because we don't quite, so they're not continuous with respect to several definitions of continuity to try to come up with, but we're not really happy with any of them. So it's still an open question whether we can find something that would work there. So that's the end.
Questions, comments?
We've more than enough time, so.
Maybe a suggestion you could point out what actually is the difficulty with non-injective algebra maps. But drawing a diagram
Well,
I would be really interested if anyone has any thoughts on that aspect.
well, this, what I said is something like, so if you have a map from A to B, and then you're defining something from from sigma B to sigma A, right? But the actual
Can you turn up the light, please?
so the actual natural transformation goes from F star sigma B to sigma A, right? And so the main problem here is so the obvious thing you can think about is to say, well, if we have a closed subset of this guy, then the inverse image by this natural transformation should be closed here. But now you have to define what it means to be closed there. And so the obvious thing you could say is that, well, there is a closed subset S of sigma B, such that just pulling back is S itself will be the guy that we get over there. So, I mean, from the closed subsets of sigma B, you can define, you could pull back these closed subsets and define a topology in this guy. But the trouble that we run into is that, so if this guy is not injective, so if basically this F from CA to CB is not injective, there are several, so the trouble again is that the thing is too restrictive, because if we have, so let's suppose we have some subalgebra C of A, and then we have some other subalgebra C prime of A, and they're not related, and both of them are mapped to the same subalgebra FC equals FC prime in B, right? And then, so what's the trouble there? If we consider a sub-object of the spectral presheaf of B, these will choose, in particular, in this context, these sub-objects will be some SC, will be a closed subset of the spectrum of FC, which is the spectrum of FC prime. So, right? And if we pull back this closed subobject, then the subobject we get in here, in F star of sigma B, we have sigma of FC and sigma of FC prime. So when we pull this guy back by F, then this SC must be replicated in both these things. Right? So you're basically forcing the object to be equal in two different algebras that are not related at all, and thus, that's just too restrictive. So it doesn't. So in particular, we'd like the context-wise topology to always capture the idea that the maps are, so this natural transformation is continuous component-wise somehow, and this doesn't happen if you do it this way. Also that, as I said, the definition that EK gives, I think, is for the maps slightly, so the maps go the other way around, so it doesn't.
When you but on the level of objects, if you have a context-wise topology and that's sigma A, sigma B, that defines a space.
Yeah.
Okay. So how about instead of writing that inverse image there, you put it on the other side as a junction at the
Yes,
take the
it's
direct
gonna be
image,
a big
and
down there.
if you have an internal space, it's a lot like an internal locale. Are these just preserved by direct image functors of geometric morphisms? In other words, it's not the case that if you look at the direct image of that you have a more or less natural topology to consider on the pushed forward of the direct image of sigma A by means of the topological structure of sigma A itself. I don't know if
I'm
the
not
words
sure.
are-
I'm not sure if that's
It's worth a try. It's definitely interesting to look at this. Yeah, I think that's definitely a doable check. It seems to me that this is a new aspect of this whole question for continuity, because we look at all these contexts and we have to take care how to get things pulled back or pushed forward on the maps. But maps may identify contexts which otherwise have no relation to each other. So this can give us trouble. In, let's say, standard alpha duality, you don't see this because your underlying posits are just points. And,
So I think you might run into the same problem because we're not entirely sure. But, so we've thought of a few of these things that we've tried and then we discarded. So I think. So I don't know,
It
can't
seems
really
like if you use direct image functors, and as long as what you're doing makes sense internally, it should be preserved. So
Yeah. Okay.
So any other questions or comments? Then I have just one comment. With this all stuff with the designisation, I often find it easier to see this topologically. So using that bundle picture of the space, what I described earlier, but also in the covariant version, you also have a bundle with the same set as total space, and usually thinking about outer dimensional projection and their relations, it's I find it easy to manipulate that from this topological perspective, so maybe you might want to look into that.
Yeah, that's good. I haven't done that.
So then let's thank the speaker again. I guess it's time for drinks. Hopefully there are drinks beyond the door.
Maybe not before we thank the organizer.
Nou, ik ben wel even die onderbreker
Dus nog steeds op maandag.
zo netjes.
Volgens mij zijn ze er. Volgens mij waren ze er vandaag.
Oké.
En anders kon je het bij de kwartier afgeven.
Oké.
Deze kan ik je nemen.
Ja, zeker.
Dat zei in ieder geval dat je die bij de kwartier kan afgeven. Met die, laat die, als ze er niet zijn.
Als ze er niet zijn, ik breng
Lever ik hem aan.
I'll take the tripod back if they're not
Ja, dat is zo drawn. But actually right.
straks. geheel volgens plan.
Goed voorbereid.
Die camera, er zit nog een opzetstuk of wat